Here we are once again. This is the Physics 2A video lecture. Physics 2A video lecture 12. And I'll start with an announcement about the remaining lectures in our semester. This is today's lecture, and we're going to finish up chapter 11. And then next week, Monday and Wednesday lectures would be chapter 12. And then end of next week, we'll have a lecture in the beginning of the following week, chapter 13. That's as far as we're going to get. We'll save the last day for a review and a general heads up. And I think we'll do pretty well. Actually, I have a couple demonstrations for you today, and we're flexible enough. If some of these days go into the next chapter, no problem. Okay, we have enough time to do this in pretty good style. Good, so where are we now? We are in chapter 11 talking about energy. So we're talking about thermal energy. And I'll just review what we had. We had a couple of interesting concepts. And of course we had the calorimetry technique. So if I go into the thermal energy, first I just talk about the calorie. And it allows me to raise the temperature of a liter of water or of a kilogram of water by 1 degree Celsius. Okay. Raise temp, kilogram of water by 1 degree Celsius. And a nice cartoon to go with that is the butter candle. Wonder if anybody went home and made a butter candle. Okay. If you haven't, try it. And then underneath there, it's underneath a beaker. We're heating water, and we have a thermometer. Okay, so there's the cartoon that goes with the whole idea of the calorie, if you know that this is a butter candle. Okay, good. So after we talked about that form of thermal energy, then we had the mechanical equivalent of heat. And this is a very important concept, so I'll write it out here. Mechanical equivalent of heat, and that is that a calorie is the equivalent of 4,186 joules. So the way to read this equation, it's a practical equation, namely the calorie represented here, whatever it takes to raise the temperature of water, okay, well defined. This side of the equation is just mechanics, okay, mechanical energy. I like as my example for this amount of joules, the stair climb. If we climb a flight of stairs, roughly this many joules, okay. And why is there an equal sign here? Because via friction, we can raise the temperature of this water, okay, via some kind of friction, internal friction. So, mechanical equivalent of heat, and I'll put here the joule churn, look that up again. But there are many ways. If you ever drive down the Grapevine, you can smell the brakes burning from the truckers going downhill, okay? They're converting potential energy into heat just by applying the brakes, okay? So it's the same friction you get when you rub your hands together and they get warm, only more so. Good, so thermal energy, mechanical equivalent of heat. Then we have, and this leads to calorimetry, we have the specific heat capacity. This is this week's lab. And I always like to have a cartoon here that, I'm, say, putting some heat. I use the letter Q into some object here, and we say that Q is equal to mc delta T. So that thermal energy is going to raise the temperature of this object here. It's got a mass and it's got an initial temperature. It's got a specific heat capacity. Okay. So yeah, this is the basis of calorimetry. So next I'll talk about calorimetry. of which I already assigned a couple of problems. But you know, you repeat this, you see it in context, and you see the logic of the whole thing. So in calorimetry, we're doing the following. We're bringing two objects together. They have initially a different temperature, and they're then going to equalize their temperatures. So the image you have is of taking two objects. You know, you could take this pen and this eraser, and one of them was in the freezer. Throw them together into cooler and put the lid on top and wait a while. That's the idea. And of course, my example was just pouring cold water into hot water or vice versa. So many, many examples. So yeah, I have some object. In fact, let's go ahead and I've had this object number 1, M sub 1, C sub 1, T sub 1, and I dump it into this beaker of water here, which is M sub 2, C sub 2, T sub 2. Okay, I dump it in there, isolate it, and then what do I have? I have Q1, let's see where we're going to work here. Send this up. We'll work right underneath. So for this scenario, I have, because no energy is being lost or wasted, I have Q sub 1 plus Q sub 2 is equal to 0. Okay? One gets warmer, one gets cooler. The energy content is the same. One loses some, one gains some. Okay? That's why we can say the total heat is equal to 0. Thermal energy is being transferred. And then we can use this equation here, and we could say M1C1 T minus T1 plus M2C2 T minus T2 equals 0. I like setting it up this way because we don't have to worry about which temperature is higher. The signs will take care of themselves. This T is the final equilibrium temperature. And in an equation like this, you can only solve for one unknown because it's one equation. So we could have Q sub 1 plus Q sub 2 plus Q sub 3 plus Q sub 4, etc. It would still just make one long equation, which allows us to solve for one unknown. Okay. So yeah, it stops being fun after a while if you have to incorporate too many things into this same equation. Good, so that's the whole idea of calorimetry. In particular, I recommend always setting up this initial energy equation before you tackle a calorimetry problem. And then it'll just flow. Okay, very well. So there's a new topic here. Our next topic, which we need to extend calorimetry. So we're not done with calorimetry, but we have to shove something in between. And that is change of phase. So change of phase, and I'll write here, we're talking about the states of matter. So what are the states of matter? Solid, liquid, gas, plasma. We're going to be primarily concerned with solid, liquid, gas. Okay, solid, liquid, gas, because we can think of water, ice, and we have water in liquid form, we can have the vapor form. So change of phase is what we're talking about when we change from the solid to the liquid to the gas. And right at the outset, we can visualize taking a piece of ice, heating it up till it melts. And we got the liquid, heating it up some more till it vaporizes, and we have the gas. So what? We're putting energy into this object. Okay, thermal energy. Okay, now the next graph, I'm going to put a pretty much full board graph here. Important one, it's in your book, you'll find it in all the books when we're talking about this business. And what we're going to have on the graph is just the energy and the change in temperature when we start adding thermal energy into a piece of ice. Okay, ice being water. Okay, so the graph looks like this. Got to leave a little bit underneath here. So what is this axis going to be? This is going to be the temperature axis in degrees Celsius. And this is going to be the energy axis, because we're adding energy, and it's going to be in joules. So let's title this Adding Energy to Water, okay, in one of those three states. So we're going to start at, say, minus 20 degrees. Imagine we have some water at minus 20 degrees Celsius. What is that? That's ice. Okay. So we have some ice and we're adding energy to the ice. Thermal energy, we're warming it up. Now, does it melt right away? It does not melt right away. First of all, you can imagine you have a chunk of minus 20 degree ice. Put it in a freezer that is set for minus 2 degrees or minus 1 degree Celsius. So that ice will actually warm up, but it will warm up to minus 1 or minus 2 degrees Celsius. So that part of this curve is that we're warming up the ice, okay? We're going to get it right up to 0 here. So now we have a piece of ice at 0 degrees Celsius. We started minus 20, and the energy involved is mass. All right, C sub ice delta T. The delta T in this case was 20 degrees Celsius. So yeah, we're just warming up ice. Now here's where it gets interesting. If we carefully add heat to this, namely slowly, what we'll find is that as the ice melts, it does not change temperature. So we'll have melting, the ice will be turning into water, we'll have mixture of water and ice, but it will still be 0 degrees Celsius. So this is called the melting. Nothing new, but what is new to us until we study the thing is the amount of energy required to melt this. Okay. Temperature staying the same, we can't use this formula down here. What we have is for the melting, Q is equal to mL sub F. mL sub F, maybe I put a red box around here. Okay. That is the mass times the latent heat of fusion. So L sub F for water, everything has its own latent heat of fusion. For water, this is 3.33 times 10 to the 5 joules per kilogram. Okay, because you can see that if the left side is joules and this is kilograms, this must be joules per kilogram. So we did our dimensional analysis right there. So that's an enormous amount of energy, actually. That's actually 3/4 of the amount of energy required to bring water from 0 to boiling, okay? Just to melt the ice. And after it's melted, it's still at 0 degrees. Okay, but finally it has melted. And now we're going to raise this temperature of the water. We're just going to add heat to it all the way until it reaches 100 degrees Celsius. Okay, and then this is just Q of warming the water, but I'll write here Q is equal to M C sub water delta T. From 0 to 100, of course, delta T would be 100 degrees Celsius. Okay. Yeah, so there's that amount of energy that's been put into the water, and now finally it's all at 100 degrees Celsius. We have what's called the vaporization. And if we do it carefully, we will vaporize all of that water without raising its temperature. Okay? Without raising its temperature. And so this Q here is M times the latent heat of vaporization. And I'm going to write these words down, but L sub F is equal to 2.26 times 10 to the 6 joules per kilogram. These are enormous amounts of energy. That's why it takes so much time and energy to vaporize water. Good, so I wanted to write this latent heat of vaporization vaporization, okay, vaporization. And this here was called the latent heat of fusion. So, latent heat of fusion. Okay, and what's so noteworthy about this is that the temperature is not changing while that's occurring. So the melting is occurring, takes a lot of energy to melt something, temperature's not changing. And for vaporization, the same thing. Okay, these red boxes look pretty good. Okay, draw attention to that. And then of course this was the heating the ice and this was heating the water. So there's a lot of energy goes into bringing water from certain temperature to another. Now, the opposite direction must also be true. In other words, if it takes this much energy absorbed into ice to melt it, it must take the same amount of energy released from the ice in order to freeze it again, right? Because energy is conserved. Okay, it just doesn't come out of nowhere and go into nowhere. It changes its form. Okay? So energy flows into the thermal energy into the ice, melts it. If you want that ice to freeze again, the thermal energy has to come out. Good, so we've got those latent heats, and this is the thing we have to add to our calorimetry problems. Say we're going to melt some ice. So I'll do an easy problem. So let's call this calorimetry example, and then we'll assign a couple to make sure you can do them. And since there's a whole chart of different latent heats, when it comes to exam time, I'll just make up a nice number, something we can do easy arithmetic with. So there won't be any problem with that way. Okay, so calorimetry, suppose we take 1 kilogram of ice at 0 degrees Celsius, take it into 5 kilograms of water at, say, 70 degrees Celsius. The question is, what's the final temperature? Find the final temperature. Okay, so let's send this up here and have a look. It's going to be the same theme as what I just wrote here. Erase this. We will say right underneath here, Q of melt ice. Actually, I need a little more room for this one. Let's start over here. So what's going to happen when I drop the ice in the bucket of water? The ice is going to melt. Then the water that used to be ice is going to heat up. So Q heat, I'll just call it the ice water. And then where's that heat going to come from? Q of the water in the bucket. And all those energies are going to add up to 0 because the melting and heating energy for the ice is coming from the water in the bucket. So they add up to 0. Now we can say mass of the ice, latent heat of fusion of the ice, okay, of water. Now we're going to heat that ice, so it'll be mass of the ice. Now it has melted, so specific heat of water, T final minus what? Well, the initial temperature of that water that used to be ice is 0 degrees Celsius. You can write it in there just to have your equation complete. And then we're going to have the mass of the initial water, specific heat of water, T minus the initial temperature of the water equals 0. Okay, so there's your equation. You can solve for one unknown. And like I said, if we do one of these on the exam, we'll just take very nice and easy numbers. I'll just make up some latent heats of fusion and vaporization if need be that are just good round numbers. Okay. Now, it's possible that if you put too much ice in the water, you're going to melt the ice, but you're going to end up with water at 0 degrees. And that's something you have to test for mathematically or arithmetically, because then your final temperature is 0, and then the question is how much melted. So for example, if I put this ice here, if I put the kilogram of ice in a kilogram of water that was, say, only at 20 degrees Celsius, so room temperature water, all of the ice wouldn't melt. Okay? And you can try those out as well. You just set up your equation, see what happens. Okay, so this will do, and I want you to be able to do this version, this level of these problems here. Set it up. I like to mix ice and water or something that keeps us from having to have too many obscure numbers. Okay, so similar to the problem we did the other day. Good, so that is the calorimetry when you're involving the latent heats. Okay, let's have a look at our timing on all of this. Okay, we're doing fine. So one more point before I move on with my topics. I'm just going to do an interesting cartoon of these whole processes. And the idea is that we take a solid, okay, and we add energy and we turn it into a liquid. Okay, so there's my block of ice, there's my beaker full of water. We add energy and we can turn it into a gas, which I'll just symbolize with a balloon here, okay? Gas particles inside. So there you go, that's solid, liquid, gas. And apparently, we're adding energy, okay? Or the object is absorbing energy. I'll just write add energy. And we're talking about the graph up there, okay? We were melting, vaporizing. So in this direction, we're adding energy here. Now, what about going from a vapor back to a liquid, going from a liquid back to a solid? All right, your solid, liquid, gas. Okay. What about that direction? This direction must release energy. So we're releasing energy when we go from gas to liquid to solid. And what's just surprising is how much energy is being released during a process like this. Over in the orange groves in the winter, say down in Visalia, cold air comes pouring out of the Sierra Nevada and threatens the citrus crop. What the ranchers will do is pour water on the ground, and you'd say, why are they pouring water on the ground? The reason is that, I'll just draw a little citrus tree here. Okay, there's a citrus tree. And okay, it's got some fruit. Now, what happens is you've got really cold air coming in down the canyons. Let's just make up a number. Suppose it has T equals minus 3 degrees Celsius. Let's get more ambitious. Say it has minus 5 degrees Celsius. Okay, it's a cold blast. Okay. What happens if there's water down here? Water at 0 degrees Celsius. That's water that's on the verge of freezing. It is going to release energy to the cold air because the air is colder than the water, right? -5 is less than 0. So what we're always having here is the energy flowing from higher to lower temperature. I'm going to be using this a fair amount later on. So the direction of energy flow, there's a Q, is from TH to TC. And you can see it even here in the orchards. You got water at 0 degrees, cold air at -5. So hopefully that energy that flows out is going to heat the air up, maybe to -1. If it heats it up to -1, then the crop would be saved. That's the idea. Okay, so yeah, that's the release of energy when you're going from gas to liquid, release of energy when you're going from liquid to solid. And that's about what I wanted to say on this topic. At the end, I'll look up for a couple homework problems. But there's our calorimetry and change of phase discussion. So what are we going to do next? The next topic is actually going to concern this cartoon here, namely the flow of thermal energy from high to low temperatures. Okay, let's go ahead and erase this here. Flow of energy from higher to lower temperature. That's the natural direction. That's you could say that's a law of nature, that the energy flows in that direction. And we'll talk about that in the next chapter as well. Right now we're talking about, so once again, this cartoon here, we're talking about heat transfer mechanisms. Heat transfer mechanisms. Okay. There are 3, and they're an interesting topic that gives opportunity for a lot of demonstrations. I brought a couple demonstrations and we'll see how those work. And so for all of these heat transfer mechanisms that I'm going to demonstrate to you, this is the cartoon I like to have. The energy is flowing from the higher to the lower temperature object. Good. So what about the first one? The demonstration for the first one is this. If there are people in the room, we usually pass these around. This is an aluminum block. This is an identical wooden block. Okay, same size, same shape. And they've been in the closet together since the beginning of time. They're just sitting here. So the closet is at some room temperature, 20 degrees Celsius, and yet this aluminum one feels decidedly colder to the touch. Okay, that's an illusion because the thermometer would tell you it's exactly the same temperature as the wood. So I'm going to do a demonstration here. I'll put these in front of the camera, but here's the demonstration. I'm going to take some ice, put a couple pieces of ice on the wood and a couple of pieces of ice on the aluminum. And now I have to move fast. Let me put these in front of the camera and try to do some camera work, because what you're going to see, there we go. What you're going to see is that the ice is melting in real time. We don't even have to wait. Whereas the ice on the aluminum is just melting. The ice on the wood block is just doing nothing. Okay. So we can hold out until the ice melts completely because it goes so fast. So those two objects, the wood and the aluminum, same temperature, room temperature. You can see the one on the left there, nothing's going on. The ice on the right is turning into a puddle, and I think I'm going to remove that puddle before it goes. So, well, now we have a little patience. Okay, so that ice is just completely melting. Yeah, so that's a property of wood versus metal. Go back to the board. Property of wood versus metal called thermal conductivity. And this heat transfer mechanism is called conductivity, or actually conduction. So heat transfer by conduction. The conductivity is the property of the metal versus the wood. Let's get this out of here. So heat transfer by conduction. And what about our cartoon here? What's warmer and what's colder? Where's the energy flowing? Okay. In both cases, the wood or the aluminum are quite a bit warmer than the ice, so the energy is flowing from that wood into the ice or from that aluminum into the ice, but the aluminum has a higher conductivity, so the conduction property is greater right there. All right, so that's heat transfer by conduction. By the way, you guys can do this at home. You don't have to have carefully machined aluminum blocks. You just take, say, a wooden cutting board. You can take a ceramic plate. You can take a plastic plate. You can take a cast iron skillet, drop ice into each one, and you can then observe the different rates of melting. That will also teach you what the best object is to, say, thaw out a piece of meat or something. You want to thaw it out. You want to thaw it out on something with higher conduction. Good. So that's heat transfer by conduction. The second mechanism is convection. What? Convection. Convection is a fluid flow. And to demonstrate this, I just brought a torch. And I'm just going to start the torch up. So that's a very hot flame. So I can barely put my hand here and not burn myself. But on the other hand, I can bring my hand in this close to the side. Okay, but so could you. It's no big deal there. You can bring it that close, bring it that close from the other side. And the reason I can do that is that there is a strong airflow. So I'm not going to draw a torch, I'll draw a candle, okay? A square candle. So good, you have a candle burning. How do you draw a flame? Okay, you have a candle burning. And if you put your hand above it, you're going to burn yourself. Put your hand to the side. What's actually happening with the candle is there is a fluid flow, namely an airflow, that's bringing in cool air, heating it up and bringing it up higher, okay? So, I'll draw an arrow there as well. And if you want to see that airflow, all you have to do is snuff the candle out, and then you'll have smoke flowing up in the direction of that airflow, okay? And we talked about fluids earlier. I think I used that example. Eventually the smoke will go up and it'll become chaotic and turbulent. Good, so that's heat transfer by convection. Oh, by the way, for conduction, I should mention how that works. It's by molecular collisions. There are many other examples of heat transfer by conduction. You know, if you take a wire and heat it on this side with a candle, with a flame, then eventually it'll become warmer at the end here. Okay. And inside the, say, piece of wire, molecular collisions are happening and agitating it, and heat is transferred from the hot side to the cold side. Good. So that's convection. The third type of heat transfer, I have another demonstration. Never done this with a camera. Let's see if it works. What I want to do is light some matches from a distance. Okay, so if this is in the picture, and if this is as well, the idea is that we have parabolic reflectors here, and I have some matches in here. I want to just shine a bright light on this reflector and light the match in there. And let's see if we can pull that off. I'll go like so. Let's see here. Okay, this is a very bright light. Let's see if we this off. Okay, bright light. There we go. Let's stand over here. Didn't take long. And I'll pull this off. Yeah, there we go. We had combustion. We had ignition. We lit the matches from a distance just using a bright light. Okay, that's a success. So yeah, what is that called? That is heat transfer. Clearly, heat was transferred across the length of the table. We can actually go across the entire room, but the way we're set up right now, the table is just right. So that is heat transfer by radiation. Heat transfer by radiation, and I have to add right away, that is what's called electromagnetic radiation. That's just light. Although you can't see all of the electromagnetic radiation, the kind you can see is called visible light. Okay, so in general, it's electromagnetic radiation. Next semester in Physics 2B, we'll talk about that some more. Electromagnetic radiation. Okay, and it's these three heat transfer mechanisms that exist. So anytime the energy is going from the higher to the lower temperature object, it has to be by way of one of these three mechanisms. Direct collision, fluid flow, which by the way really carries a lot of heat rapidly. The fluid flow does, and then the radiation as well, electromagnetic radiation. You may have, if you have a powerful incandescent bulb and you switch it on, you could, from a distance, you can actually feel the warmth on your hand immediately. That's the radiation. It hasn't had time to conduct over, you just feel it like that. Good, those are the three heat transfer mechanisms. There are some formulas that we could introduce. I'll just do the conduction to make sure we have it in our notes. So what we have is the power transformed, Q over T is Ka delta T divided by L. So this is the transfer of heat across an object of cross-sectional area A and thickness L. I'll get that right. Okay, so imagine you've got a slab here. You've got an area A, you've got a thickness L, and the substance, so that's what A and L. Delta T is the difference in temperatures between one side and the other. Okay, that's the difference in temperatures. And K is a material constant, okay, the conductivity. So that's the formula for that. The radiation law I'm going to put up here as well. Yeah, so the radiation law is actually some more advanced physics. But the power radiated, so we would have P in watts, and the idea is we have some object temperature T, and it's radiating energy in every direction, okay, like that light bulb was, like the sun, okay? So power radiated is equal to sigma E A T to the fourth. And if you have an incoming and outgoing radiation, I'll give two different colors here, incoming and outgoing, due to different temperatures, then we would have T to the fourth, all right, minus T0 to the fourth, and that would be the net power radiated. So what there is absorption and emission. Okay. So if you just want the pure emission, you're just talking about the t to the fourth. For example, a really hot object where this t to the fourth completely negates this one. Okay, we have the Stefan Boltzmann constant. Stefan, and this E is the emissivity. Okay, so what I think I'll do, and you look this up and you'll, excuse me, look this up and you'll get the values of these. I think I'll put one of these on the homework now just to make sure you guys get a second look at it. So let's take a quick look at what we have here in chapter 11. Add a couple of problems, and then we'll be done for the day. Okay, so yeah, this is Stefan's law, by the way. So let me go ahead and write that down. It's not the net there, it's just sigma E A. By the way, this is just a number between 0 and 1, but it'll be closer to 1 for normal object. Sigma E A T to the fourth, Stefan's law. Now, we're mainly interested in an extra calorimetry problem with the latent heat. So let me write here homework for chapter 11 and see what we get here. Ah yes, number 27. 27 is just what I set up. Okay, just the one I set up. And we'll just add a couple more. And 29, also the kind I like. Ice in water, final temperature is asked. Okay, that plus the ones I set up in class are good. In terms of the Stefan's law, would be a good one. Yes, this is a great one. So this problem 71, let me even read it to you. It says the surface of the sun has a temperature of 5,800 Kelvin. Good point here. These temperatures are in Kelvin. T in Kelvin, important right here, okay. So the temperature of the sun, 5,800 Kelvin, gives you the radius of the sun. You assume the emissivity of the sun is 0.986, which, like I said, very close to 1. And then they want you to calculate the total energy rated by the sun each second. Well, what is the energy per second? That's the power in watts, okay? Joules per second is watts. So although that's just a plug-it-in problem, very interesting. Okay. Possibly I'll have a chance to come back to that. There was one more I was interested in. Yeah. But right now we're going to leave it at that. And I won't assign anything till next week. This is the stuff that's due next week. This is the last lecture of this week here. Okay. None of that up there. Good, so keep taking good notes, try out these homework problems, and see you next time.